Good evening, everyone. Thank you very much for attending our joint webinar session between Orthopaedic Academy and Orthopaedic Research UK. Today, we're really grateful to have Professor Emad Saweeres doing his presentation on tribology, a very important topic that will come up quite a lot within the basic science part of the Viva, and also a very key component as part of our day-to-day work in arthroplasty. And I would advise you to listen very carefully and take note of a lot of the important things that will be discussed today. This will take around half an hour or so. There'll be a poll of questions in between to make sure people are paying attention. But please also, if you've got any questions, can you put them in the chat box? And for us, we'll take note of it. And after the presentation, we will go through the questions people have got to ask. We'll also do, afterwards, we'll do a hot seat practice Viva with 3 candidates, where we'll try and discuss some of the tribology and basic science components that have come off today. And we'll do this in the style as we've done before, where we'll have 5 minutes for questions and feedback from people doing the questioning. And hopefully this will take, we'll be able to finish at 8:30. So without further ado, I will hand you over to Professor Saweeres.
Thank you very much. So good evening, everyone. It is my pleasure to meet you once more in the first webinar for the year 2022. We will take off where we left last December. Having covered the principles of biomechanics, we are now aiming to venture into the topic of tribology. My name is Emad Saweeres, and I am one of the orthopedic doctors at El Sahel Teaching Hospital in Cairo. When the internet community was asked what tribology was, all sorts of bizarre definitions came out. While tribology has definitely nothing to do with 3-legged races, it is the study of interactions between 2 solid surfaces in relative motion. Biotribology, in turn, is tribology borrowed by biologists from engineers. Different combinations of friction, lubrication, and wear are required depending on the desired interaction of moving objects. Therefore, by the end of this presentation, you shall be able to describe the principles of friction, lubrication, and wear, and apply them to our natural and artificial articulations. If you have attended the last webinar on biomechanics, the following example should be familiar. Take this block, which has a mass of m. Under the effect of gravity, it pushes on the surface with a force equal to its mass multiplied by the acceleration due to gravity. According to Newton's third law, the surface is in turn pushing against the block by an equal and opposite force, called here force normal, being perpendicular to the surface. If we start to tilt the surface, the force due to gravity will remain in the vertically downward direction. However, the force normal will have to remain perpendicular to the surface. To estimate this force, we resolve the force due to gravity into its components. Although the force normal will consequently become smaller, however, the parallel component of the force due to gravity will attempt to move the block down the slope. Being opposed by an equal and opposite force, the block remains in equilibrium. This opposing force is the force due to friction. The more you tilt the surface, the bigger the parallel component of the force due to gravity becomes, and hence the force due to friction would have to increase in order to keep the block in equilibrium. So, as the parallel component continues to increase, the force of friction will also increase from 0 to a maximum in order to keep the block from moving. There is going to be a point where the force of friction will not be able to resist the moving force, at which point the block will start to slide. It is obvious that the block will start to slide at a smaller angle if the surface were rough as wood, for example, compared with a smooth surface such as glass. The force due to friction will obviously depend on the nature of the two interacting surfaces. The heavier the object, the more difficult it would be to move. Friction is therefore a force that resists relative motion between two interacting surfaces, either due to adhesions caused by surface roughness or viscosity of the shearing lubricant film between them. There is another type of internal friction which occurs inside a material or structure and is not considered in this lecture. We have seen from the previous example that the force due to friction is proportional to the normal loads on the surface. Friction does not depend on the contact area or sliding speed of the two surfaces. Therefore, the contact area between the surfaces can be increased to reduce the pressure without increasing the friction. The coefficient of friction, mu, indicates how much force per unit load is required to initiate sliding motion between the two surfaces. It has no units and depends on the roughness of the interacting surfaces. It takes more force to initiate than to continue sliding. Hence, the static coefficient of friction, mu s, is always larger than the dynamic coefficient of friction, mu d. The typical examples in the table indicate the coefficients of friction between your car tire and the ground, train wheels and the railway, metal on polyarticulation, and metal on Teflon, which is PTFE. Given its low coefficient of friction, it is no wonder that Sir John Charnley chose Teflon to make his early acetabular cups. The disadvantage of Teflon will be explained later. Since no surface is perfectly smooth, areas of surface roughness, alternately called asperities, result in localized contact between any interacting surfaces. The true area of contact is therefore proportional to the normal load and inversely proportional to the hardness. Under very high stresses, the summits of the asperities bond together, the bond strength being proportional to the true contact area. Based on what we have learned so far, consider this question. Assuming a similar combination of interacting of blocks and surfaces, which block experiences more friction? Please vote. Absolutely brilliant. The block in figure C is obviously larger than the other two blocks. Since all blocks have a similar material, its mass is bigger, hence the normal load, which is proportional to friction, will be larger. Coefficient of friction is the same for any two combinations of materials. The surface area does not affect friction, which depends on the true contact area and hence the normal load. In addition to causing wear of the moving surfaces, friction increases the load at the bone implant interface, which might result in loosening. Friction force itself is proportional to normal load on the implant and does not change with different femoral head sizes. On the other hand, frictional torque on the acetabular cup, which is proportional to the coefficient of friction of the articulating surfaces as well as the head diameter, increases with the larger femoral head size. Figures in the table show why Sir John Charnley elected to make his femoral heads as small as 22 millimeters. At the bottom row, the advantage of initially selecting Teflon with a very low coefficient of friction in combination with a small femoral head is clear. We have so far considered the principles of dry friction. The addition of a fluid between the two surfaces with its low shear strength results in motion within the film, hence reducing friction and wear. We have all experienced how the car tires on the first row skid on a wet ground or a wet road during rain. Although the coefficient of friction in artificial joints is markedly reduced in the lubricated state, it is still nowhere near that of the natural joint. This brings us to the topic of lubrication. A lubricant is a substance introduced between the sliding surfaces in order to reduce friction and wear. It could either be a solid, liquid, or gas. Interacting surfaces need to slide relative to each other at a reasonable speed in order to maintain an adequate fluid film. This is much like water skiing. When the skis are initially stationary, the skier tends to sink in the water under her weight. However, once the boat starts to pick up speed, she is kept floating by the velocity of the boat and the viscosity of the water. The slope of the ski is represented by the clearance between the acetabular cup and the femoral head. At both ends of the spectrum, we have the two surfaces either in contact with each other, being covered only by a very thin film of fluid, or completely separated from each other by an uninterrupted fluid film. Increasing load will shift the conditions towards boundary lubrication, while increasing the velocity of motion, viscosity of the fluid, or effective radius would foster hydrodynamic lubrication. When the fluid film between the interacting surfaces is about the same thickness as their surface roughness, asperities on the opposing surfaces get in contact, resulting in a high coefficient of friction. On the other hand, fluid film completely separates the interacting surfaces in hydrodynamic lubrication, such that any motion occurs between the layers of the fluid film. The slope of the ski in the water skiing example represents the radial clearance of the implants. This is the degree of mismatch between the radius of the femoral head and the acetabular cup. Clearance determines the effective radius, which in engineering terms is the radius of the ball when the ball in the socket is converted to a ball on plane. The fluid film thickness depends on multiple factors. As in the example of the water ski, it increases with the increase in the viscosity of the lubricant, the relative velocity of the surfaces, and the effective radius. The fluid film thickness decreases with the stress across the interface. Contrary to friction, which is independent of the contact surface area, lubrication of the larger head is much better than that of a smaller femoral head. The above factors describe what is called Summerfield number, or the film factor. Because the relationship between coefficient of friction and bearing parameter is complex, it is easier to present it with a curve rather than with an equation. When articulating components are stationary, the coefficient of friction is relatively high, and the components are only separated by thin fluid of film, what is called boundary lubrication. As the components start to move relative to each other, the coefficient of friction drops as the one component starts to float on top of the progressively thicker fluid film. In the hydrodynamic region of the curve, although a fluid film completely separates both components, the coefficient of friction starts to rise slightly because of drag between the layers of fluid. Because of the surface roughness of polyethylene, hard on soft articulations like metal on poly can only have boundary lubrication. Hard on hard articulations, on the other hand, experience mixed and fluid film hydrodynamic lubrication. In order to move from 30 degrees of flexion to 15 degrees of extension, a small femoral head would have to travel, a short distance to cover its 45 degrees angle. A larger femoral head, in contrast, would have a larger sliding distance to cover in the same range of motion in the same time. Although the larger head has an advantage in terms of better stability and range of motion, because of the larger sliding distance, it also has an increased wear rate. On the other hand, because the larger effective radius and high velocity, the larger femoral heads are more suitable for hard-on-hard articulations where mixed and fluid film lubrication occurs. This advantage is not experienced by the hard-on-soft articulations, which can only be lubricated by boundary lubrication. Another advantage of the larger heads is the reduction of stress due to a larger area of contact, thus enhancing fluid film thickness. The initial combination Sir John Charnley used, a 22 millimeters head with metal on polyethylene articulation, resulted in high wear and less stability. Increasing the head size to 28 millimeters increased the stability at the expense of wear. Changing the articulation into highly cross-linked polyethylene has definitely reduced wear rate. Increasing the head size to 36 millimeters proved to be a reasonable compromise. On the other hand, hard-on-hard articulations have shown reduced rate of wear. Using a larger head in this type of articulation definitely increases the stability without affecting wear very much. With our knowledge about lubrication so far, I would like you to think as to which mechanism was related to failure and device recall in the case of the ASR hip resurfacing. Please vote. Explain the question a little bit at a time. The correct answer is B. The ASR acetabular cup had an inside groove against which a surgeon pressed a tool to implant the component. The groove limited the surface area inside the cup. As a result, the ball was more likely to strike the cup's edge, causing wear and generating metallic debris. This was particularly prone to occur when the cup had a more open inclination. Figure A shows the adequate clearance with polar bearing of the articulation. Figure C shows equatorial bearing, and figure D shows fully congruent articulation. In both cases, there was no clearance for the fluid film movement inside the hip. So what you want is an adequate clearance like in figure A. That brings us to the discussion on the topic of wear. Wear is the progressive loss of material as a result of relative motion between articulating bodies. It results in a change in the shape and size of the objects and produces wear debris. As in the program weakest link, it is the softest and weakest material that usually suffers the most. There are four general subject areas in relation to wear: wear modes, wear mechanisms, wear damage, and wear debris. In mode 1, wear occurs between two primary articulating surfaces. Remember, primary versus primary is 1 times 1 and is equal to wear mode number 1. In mode 2 wear, a bearing and a non-bearing surface are rubbing against each other. Mode 3 occurs as a result of third body particles, and mode 4 occurs between two non-articulating surfaces. Remember, secondary versus secondary, which is 2 times 2 equals 4. Examples include mode 1 normal wear that occurs between the femoral head and the acetabular liner. Mode 2 is represented by microseparation and stripe wear between the femoral head and the non-articular edge of the acetabular liner. Mode 3 is the third body adhesive wear, abrasive wear, and mode 4 here represented by impingement between the femoral neck and the edge of the cup, or the backside wear between the liner and the shell. The previous wear modes can occur because of any combination of the following mechanisms. Adhesive wear results from the formation of spot welds between the two surfaces with subsequent breakage of the transfer film resulting in third body particles. Abrasive wear is similarly, it's like using sandpaper where asperities on the harder surface causes plowing of the softer one. Fatigue wear results in subsurface cracks, which eventually communicate, causing delamination. Thus, the primary wear mechanisms can either result from low-rate abrasive wear, which does not involve transfer of material from one surface to the other, adhesive moderate-rate wear, which results in transfer of material from the softer surface to the harder one, or high-rate third-body wear. Adding corrosive wear to any of the three mechanical wear mechanisms result in marked acceleration of the process. The above mechanisms result in change in texture of the shape or the shape of the implant. The resultant damage has been expressed by a long list of descriptive terms. Wear generates billions of particles which initiate biological reaction. Local effects depend on the size and number of particles, which either macrophage activation leading to granuloma formation or lymphocytic reaction resulting in pseudotumors. The smaller metal ions could escape into the systemic circulation, resulting in carcinogenesis or teratogenicity. Here is another poll question. In which articulation do wear particles result in granuloma formation as a body response, leading to osteolysis? Please vote. The correct answer is C, where the polyethylene particles are known to cause macrophage activation and granuloma formation with osteolysis. Metal-on-metal articulation in figure A usually result in lesions such as pseudotumor, alval, or ARMD, while ceramic-on-ceramic articulations are biologically inert. Linear wear can be measured on X-ray or other special techniques by head penetration in millimeters or millimeters per year. Volumetric wear is measured or calculated in millimeters cube or millimeters cube per year using simplified equation, assuming that the head produces a cylindrical bore. Many of you will be familiar with this illustration, which shows how much wear volume is produced by different combinations of bearing surfaces. It is, however, the size and number of particles which determines the biological effect of the wear debris. Although the volumetric wear is much less in metal-on-metal articulations, particle size is much smaller, sub-micron, resulting in billions of particles being produced with each step. Debris production is initially accelerated in the initial wearing-in phase. However, it later reduces and reaches a steady state. Wear volume is directly proportionate to the normal load, and not the stresses, and the sliding distance that the articulating surfaces experience. It is inversely proportionate to the hardness of the softer component. Using this information, one can calculate a unitless wear coefficient as well as a more specific wear factor. This is where the disadvantage of Teflon becomes clear. Its wear coefficient is far below that of metal on polyethylene. This explains Charnley's decision to move from Teflon cups to polyethylene ones, which we nowadays use. Ceramic-on-ceramic articulations are by far the best ones at present in terms of wear factor. In order to reduce wear with its inherent problems, one could either improve the existing material, for example, reducing oxidation of polyethylene by remelting or annealing, or increasing its cross-linking by low dose or sequential radiation. Ceramics have evolved from zirconia, which has largely been replaced by alumina and delta ceramics. Another approach is to introduce alternative bearings, such as ceramic on highly cross-linked polyethylene, metal on metal, or ceramic on ceramic. Tailoring the implant geometry to the type of articulation and its lubrication, and improving the radial clearance will result in reduction of wear. So in summary, ladies and gentlemen, friction results from interactions at the contact points. The thickness of the fluid film determines the type of lubrication and is determined by the speed, viscosity, and force applied to the articulation. We also discussed wear mechanisms and the local and systemic effects of wear debris. Thank you very much.
Just a quick one to remind people of some upcoming courses. So this Saturday, we have an intensive FRCS mock exam. We have several more dates as well coming up, all in preparation for the Viva. We also have case-based discussions for the FRCS, again in February, March, April. And we also have a basic science course as well, one coming up at the next weekend, 29th of March. So please go to the Orthopaedic Academy website to get more information to book and contact through the email to let them know if you're interested. Okay.
Thank you very much, David. We have one question I've come across, Prof, to you.
Yeah.
And just my comments, the lecture was very comprehensive, exactly at the FRCS level, and probably at the level of some of it is higher level, like, you know, scoring 8 in the exam. So it's definitely at the right level for the exams, for those aiming high. Lots of concepts, complex concepts they're explained. I've really learned a lot. I just want my comment to the candidates is that tribology, biomaterial properties, wear, osteolysis, and lubrication are very, very well, very, very close together. And you could take the questions and ask about any of these in any of these 4 or 5 directions you want. So examiner can put a material, or can put a failed hip replacement or a failed knee replacement, and you could take it wherever you want. You could start talking about the lubrication, osteolysis, wear. All of these concepts are connected very closely, and the examiner also can ask you about any of these. So they are very connected. Make sure you're able to go through these if the examiner wants to change the direction. We have one question for you, Prof. Is they wanted, Ethan asked, he wanted a bit of more clarification on the question number 2.
Remember, we talked about the fluid film and that you have to have a slope like this ski slope between the edge of the water and the moving edge of the implant. And we have said that this is measured in engineering terms with the effective radius or the clearance. So you always have to have a slight mismatch between the head and the cup itself. If you have exactly the same radius, this would be similar to the figure D. Figure D, the cup and the head have exactly the same radius of curvature, which means that there is no fluid film. They get stuck together and they will not move. Similarly, if the head is larger than the cup, then it would be jammed at the edges, which is what we call equatorial bearing, that is figure C. So at the equators, you'll have contact. There is a space in the bottom of the articulation, but because of contact at the equators, there is no movement and no fluid film. The best idea, or the best tolerance, is when you have the status at the figure A, where there is a slight space or slight mismatch between the head and the cup, and the cup is bearing at the bottom of the articulation, which is called polar bearing. So fluid can get access, and as you start moving, even the polar bearing, which starts off as a boundary lubrication, will be converted to a fluid film as you increase the velocity of movement of the cup. What happened in the ASR cup is they manufactured the cup with less than 180 degrees of coverage. And this coverage was reduced further by a groove inside where you can apply the tool or the impactor for the cup. So the effective surface which is available for the head to articulate with was reduced. So this would lead to edge bearing. Add to that, if the surgeon implants the cup in slightly open inclination, like 60 degrees instead of 45 degrees, as in figure B, then the polar bearing becomes edge bearing, and this increases the stresses, causing lots of wear debris and metal ions coming into the circulation. And in fact, these hips kept on failing in the first 5 years and had to be abandoned at the end. I hope this is clear.
Yeah, that was clear. I think it comes into the exam this is an advanced question really. And you will be asked this only if you're doing very well. Once you've gone through the different types of lubrication, surface material properties, and then maybe the examiner will ask you about this, why ASR has failed, and you can apply those. So make sure, guys, you get this lubrication, different type of lubrication and surface properties right first. These are the basic principles we focus on. And I think there was another question. Ethan says thank you. He's got it. And
thank you, Ethan.
And I think they want a bit more clarification about the question number 3.
The only problem is that David will not be able to ask that in the Viva afterwards.
Right.
Because they will not
question. Don't worry. Don't worry.
Excellent.
We can always, yeah, can't keep.
Right. I'll share the screen again.
How is the reaction between metal on poly different from metal on metal? I think that's
right. Remember that the size of the particles is bigger in the metal on poly than metal on metal. The particles in metal on metal on poly is a 1 micrometer particles, while those in the metal on metal is 0.1 micrometer. Consequently, there is so many of them in the metal of metal compared with the metal on poly. But it's not the number of particles only, but it is the size of them. The larger ones, which is the 1 micron particles resulting from metal on poly articulation, are engulfed by macrophages. And macrophages cause this granuloma formation. They release the cytokines and cause the osteolysis. While the smaller particles, the submicron particles of metal on metal, these are effectively metal ions, and they do not get engulfed by macrophages. They initiate a lymphocytic reaction, and this lymphocytic reaction, which is called alval or lymphocytic or accelerated rate metal debris or accelerated reaction to metal debris. This is what causes the pseudotumors, and they start destroying the local tissues. It also goes into the circulation, and there is concern about the carcinogenicity and the teratogenicity. So size of the particles, which cells respond, is it macrophages or lymphocytes, determines the local reaction.
Brilliant. That's wonderful answer, Prof. I think as a very good question from Bilal as well, trying to clarify this. So I think, I hope you got that. I think I definitely did. And that's clear what type of the size of the particle, and then that attracts different cell types. So that's very well explained. I think this is very, very complex concepts. It's very, very difficult to get them completely 100% right, even if you've done a PhD in engineering. And how to apply them to orthopedics is also complex. So try to simplify these and might understand the different type of lubrications. There are lubrications in natural joints, different from lubrication in artificial joints. Yeah, I think that's very poorly explained in many books where they mix them up. And you just need to understand lubrication, types of lubrication in natural joint is completely different from artificial joints, guys, okay?
I left it out, actually, the natural joint, because of the weeping and the...
Absolutely. Absolutely. You know, they're completely separate. A lot of people mix between them. Yeah, and thanks, Carl. Yeah, it's adverse reaction to metal debris.
Adverse reaction to metal debris, yeah, exactly.
Okay, yeah, adverse reaction to metal debris is, yeah. Jishan, yeah, thank you, yeah. So these all terms as well, ALVAL, ARD, ARMD, pseudotumors. We get asked about them a lot, what exactly the difference is between them. And I think for the FRCS exam, you don't have to worry. There could be difference. Yeah, there could be tiny histological difference, you know, and that's, you have to be the, you know, the top of in
I mean, the key thing
analysis.
Yeah, I mean, the key thing is understanding the difference is with the traditional polymetal, it's macrophage mediated. With metal, it's lymphocyte mediated. If you can get that message across, they're happy. That understands the basics. And then equally with both those questions, it's a case of demonstrating that you can apply your basic science knowledge in a clinical situation, which is what for us we're talking about, pushing on to a 7 or 8 in terms of the Viva score. And that's a very important thing that they want you to show. I mean, it's in the clinical sort of Viva, it's the reverse. If you can apply a basic science to a clinical scenario, they're very pleased to see that. But certainly in the basic science table, they want you to demonstrate how you can apply a basic science situation in the clinical. Okay.
Yeah. If I may add, the lymphocyte-mediated ALVAL or ARDS is not only limited to metal-on-metal articulations, but it also occurs in trunnionisis. So this is one of the buzzwords or coming up in the literature now. So you have to know that there is slight movement between the trunnion or the Morse taper and the metal head, and this slight fretting movement would cause metal ions to be released and could also cause pseudotumors.
Yeah. So so one pitfall I find candidates falling into this types of lubrication between mixing up between natural joints and artificial joints. The other pitfall is some people mix up between mechanism of wear and modes of wear. Okay, guys, I'm sure you all know it, but just make sure when that comes to you in the exam that you don't mix them up. There are mechanisms of wear and modes of wear. Prof. Saweeres went nicely through the mechanisms of wear, explained them beautifully. Just guys, make sure you don't mix between these two. Yeah. Any more questions? If anyone wants to speak or write their questions, please feel free. There's no, as David said, there's no stupid question at all. You know, feel free. We are all here colleagues. We've all been through this. We understand where you are, where the questions are coming from. So please feel free to ask. And our job here, we don't know any more than you. Our job is just to direct you to how to answer your exams and answer questions in the exams. That's all.
Yeah.
And again, also, any more? We've got one volunteer for the Viva. We need a couple more.
Yeah.
Anyone's keen.
So anyone wants to Viva, please as well. The Viva station which gonna connect is not recorded, and we will understand how stressful it is. And I think it's very useful. We always get very good feedback, and people always come back for these Viva questions because how useful they are. We give you feedback, and we tell you how you should answer these questions, and we give you